Welcome to a new test and teardown video. Yes, another HP frequency counter. This one is a 5512A. So it's very similar to the previous one, but there's only one input, and so it can't do any period timing, this versus that and so what. But of course it can measure on this single input the frequency and the period time. The fan was a little bit stuck, so I gave it some drops of oil and I've been exercising it a little bit, so I hope it's gonna spin when I power it up for the first time. I also see a little bit of corrosion on some of the components here, so I am a little bit worried about what is going to happen. Mains is on, and I did verify there's no short circuit from the mains input to chassis, so we should be safe to do this. Ooh, the fan spins. So far, so good. No smoke. 27 watts, and that is so far. Oh, look at that. 1 second, we got some. No, I was sure I saw some blinks. Okay, here we got some blinks in 0.1, but what in you? That is definitely a problem. Okay, so there's some stuff with the gating. It's quite easy just to look at the... Okay, and then they go... That is not how it's supposed to be. I found the problem. It is like almost always a capacitor. So there's a minus 50 volt supply, and this capacitor was just non-existent. And this is actually the voltage that goes to this transistor. See, this is the same blue wire. So then there is a regulated negative supply that drives almost everything. So that is why it was not counting and it was not doing its thing. And here is one of the counter modules, and this is exactly as the previous video I just released. So please look at that if you want to know how this one works. This is exactly the same. So we got the 4 counters. So this is the 4-bit counter and the 8 neon bulbs and the light sensitive drivers for the Nixie. And the decimal point is here. And the Nixies in this one, they're quite a lot bigger. So they are called ZM1022, right? Yep. Really a beautiful Nixie tube. Sometimes you see a date written here, so you can see exactly when this was manufactured. But I don't understand this 14.1 or 14.24. I don't understand exactly how that is supposed to be. What is that? So the back side of the unit with the bottom plate removed, of course, so we can see all the plug-in modules connectors. And this is the crystal, and the crystal oscillator is of course here. So this is the input connector, sensitivity pot, and then it goes via a capacitor to the amplifier and trigger. Yeah, power supply uses a little bit thicker wires. And here we got some power transistors. So I'm mounted here for cooling. And here's a view of the top. I took out one of the modules just for inspection, but everything here is very much the same as all the other counters. There's one thing I don't know if I like this about this counter. See, here is mains entry, but the transformator is here. Power supply is here, and they took the crystal oscillator furthest away from the power supply, so that looks like a good idea, right? But here's the input, and this is the highest digit, this is the lowest digit, so this is where the gate is, and this is where you want your highest frequency of your oscillator. So in the other HP counters, they've done it the other way, so you don't need to reroute higher clock frequencies. So they put the clock oscillator in this area, transformator and power supply up here. So there's a natural flow of signals through the counter modules. That is a little bit smarter. So here's a little bit different, the same fan. Ooh, this one goes really. This needs a drop of oil. This one was probably stored in a place with a little bit too much humidity. So look at that, quite corroded. That is not so good, is it? And this is the gate board, again with the 2N169A. But look how corroded the pins they look here underneath the transistors. Like very corroded. Even I think this one's like green corrosion. Ooh, yikes. So that is a little bit bad. But what this is, okay, so it's gold on one side, gold plated. So look at that. So when it's gold, it is just looking like brand new. But tint also works. Somebody changed the transistor right here. Oh, that one was changed or resoldered. Really? Is this supposed to touch the other one? Well, there is a 0 point nothing distance there. So I've just put another capacitor in parallel with the capacitor that is not working anymore, just to prove that it is working. I've been playing a little bit with different frequency measurements, and I found the most significant digit was not working correctly. So I started to write down exactly what happened to see if I could figure out if there is anything special. And it was the number 2 and it was the number 8. They were not working. And so to prove if it is only the readout or the counter or where exactly is the problem, I started to swap the two Nixies, and that was exactly the same. So it was not the Nixie tubes. They can actually be defect in some of the digits that don't light up or is shorted or other kind of things that can happen. And so now I've marked. See, there's a okay. It's not impossible. It's not easy to see. Anyway, I swapped this with that one now just to prove if it is the counter that is wrong. And now I'm putting in 1, 2, 3, 4, 5 hertz. Obviously, just to see if if I can prove this is a counter kind of thing. And so if it's skipping a 2 and 8, I will be missing 2 in all the higher digits, right? Because what counts in goes out again. So I know now that this module actually also counts 10 all the time. So all the counters, all the transistors, all that stuff is definitely working. So far, so good. So what if I change the number 4 here to 3 and then 2? See? So this is the number 2 that is not working. And then it looks like that. Or if I go to number, so that is number 7, and then 8. See, again, 8 is not working. 9 is working. Good. So it has to be something with either the neon bulbs or this light sensitive resistor network that actually powers up the Nixie. So to fix this, I need to completely disassemble this unit and see if there's anything in there that's not working. Oh, it's not going to be easy. And now we're in. And this is where all the magic happens. Here we got the 4 binary counters consisting of 2 and 2 transistors. And here we got the 8 set of multiplexed diodes, or they're actually counting in this little bit special binary format they invented for this project. And then in here we got the resistors. They're connected in a special way so that when the special binary code exists, the correct digit on the Nixie shows up. So this is actually a binary to decimal converter, and on the back side of this white ceramic plate we've got some light sensitive resistors. So this is the internal of the secret parts. Again, you can imagine those 8 bits, or I don't know exactly if I will call this 8 bits, but this is kind of a multiplexed output of the 4-bit converter or counter, right? That drives those neon bulbs. And now those neon bulbs, they hit the resistive sensitive arrays here. And as you see, sometimes we got 2, then we got 3, and so on, right? And there's actually a little, this dark this is a little light isolation thing that is here in the middle. That is so no light from the wrong bulb is going to go into the wrong room, so to speak, and hit the other light sensitive elements. So what I really wanted to do here is I wanted to remove also the decimal point and then plug this in and see if they all count in the right way. So is it a neon bulb issue, or is it here, the sensor? Because I did already swap the neon or the Nixie, so I know for sure the Nixie is okay. But how can this be wrong? We got some connections through this ceramic. Maybe they don't have any good connections anymore. So there's a special film coating. This is all sorts of a coating thingy on this ceramic. I don't know how to debug that. So I go for the easy way. Which one of those neon bulbs are not working? Here is another little trick to debug neon bulbs. See this one? See? So here's what I can do. I don't even have to touch them. See? I can prove all the neon bulbs, they're working. So this device sent out a high frequency, high voltage pulse on its antenna, and this will activate the neon in stuff like this, or of course it will also activate Nixie tubes and such. But I know the Nixie tube works, so now I also know all these works, and I did actually measure all the diodes here, they work. So what else can it be? How about I just plug this into the machine and then see what happens. I'll try and show you guys exactly how I debug this. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and back to 0. Fantastic. I must say I wasted a few hours screwing around with this module. So it is now still number 2 and number 8 that is not working, and in the highest digit. And you know what? This is 302 kilohertz. Okay, so if it is 202 kilohertz, you want to say, or let's say 2, 3, 4 kilohertz, right? So it looks a little bit better. Then it's easier to see what's going on, right? So if I want to show this with a higher resolution, obviously now I'm going to lose the number 2. You see what I'm saying? But I can just go back and get my number 2 back. So I can actually survive without this number, right? I can just carry on really and get higher and higher resolution if I want to. It doesn't really matter if there's an overflow here, right? So this counter was specified for 300 kilohertz, like this, right? And what happens with the 300 kilohertz? That means it must be in times 1, right? Or must it be in this, so you see the 300? I don't know, really. Well, let's try something more fun. 400 kilohertz. Well, let me give it a little bit more. Okay, 400. Good. Now we're happy. So this is more than specified. 500. 600. Let's try and push it a little bit. Ooh! Are we having problems? But 600, okay, so 600 works, 700 don't work. But what if I do like this? Nope, still don't work. Okay, so that is how it is. It actually works 600 kilohertz. That is pretty good. Yeah, it does. So that is how it is. I forgot to show the period time. I really like how fast it goes. So this is 1 kilohertz of input. See? So that means this is 1 millisecond. It's just so insanely fast. Okay, if I want to go, okay, so let's give it 10 hertz of input. Obviously. Where's my... 10 hertz in. I should of course go to square wave, right? To get a reading, should I? Let's go here. See if I get signal. Okay, so this thing don't work with 10 hertz. Really? Yeah, of course it does. See? 10 hertz. So, because this is kilohertz. I'm not showing where my fingers are. So this is 1 kilohertz, 100 hertz, 10 hertz. Okay, so far so good. So that means I got an input, right? Microseconds. Okay, here we go. So milliseconds is here. So this is 100 milliseconds, that is 0.1 second. Exactly what we got, because we got 10 hertz of input. I think it's still quite sexy with all this resolution. So this is, if this is 10 hertz and 10.01. Isn't that cool? Oh man, I got really good resolution and really fast update. There's just some, this can just do some nice things. Anyway, I think we're not gonna play anymore with this, and of course we're gonna get even higher resolution every time you do this, and la 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 la. You got the point, right? Okay, thank you for watching. See ya. So this is the capacitor without any capacitance. Ooh, 0. No wonder we had a lot of ripple and everything was going crazy. Yep. And look at that. Let's see if I can get some light here. It's a Sprague and it says 500. And I think this is 75 volts DC. I wanted to see if I could get the capacitor out of this holder, so I could maybe hide the new one in here, so I could keep this counter original looking, at least, because I'm not able to get a capacitor that looks like this. But I really like this old paper look. But wouldn't it be a little bit of a shame just to put in a new plastic? This doesn't really look like nice, does it? So how do I do that? I don't want to break the... There's no way I can push this out. Damn it. After a long time of fighting with this, I finally gave up. See what they're doing? They glued them together with something that looks like tar. Really? Why would you do that? This is impossible to get in here, man. No. I'm sorry, this is tar. Can you come up with a better fire starter for any kind of fire? Paper, tar, heat this up. Broken capacitor that gets insanely hot. Nah, I can't imagine that is a good idea. Let's try and do that. Oh, this is a catastrophe waiting to happen. Bad idea. Now I know why we got 0 capacitance left. Look at that one. The acid in here just ate the electrode. And I don't know if you can imagine the stink of this. It is tough. to say it.